Having solved the model, we can open up the Output Manager and look at the voltages and the electric contours. So if we click on Show Step 1, and there only is one solution so far, then you can see the electric field on the left and the voltages on the right. The voltages go from the high applied voltage down towards ground from the top cap to the bottom cap, and you will notice that the voltage dies off very quickly around the top cap, and that's reflected in the field by the fact that the field is highest very close to the top cap. So for this situation where permittivity is dominating, then we see that the electric field is very high right by the top cap and very small as we go down the sheds. Now let's change the material, and if we compare the glass and the copper that we're using here, you can see the glass has a conductivity of 1e to the minus 14. The copper has a conductivity of 5e to the 7th. That is, there is almost 22 orders of magnitude difference in the material properties. So the question is, what actually makes something a good or a bad conductor? There's a lot of difference between these. So if we modify the glass to find something somewhere in the middle, let's edit the conductivity to be 1e to the minus 4 instead of 1e to the minus 14. So we'll do that, and we'll run the same analysis again and then compare the two. Note that 1e to the minus 4 is still something like 11 or 12 orders of magnitude more insulating than the copper. So it's still a vast difference as compared to the copper. So now we can look at the voltage and the field both for the initial problem, this is the plot we saw before, and for the much higher conductivity but still quite insulating situation we changed it to. And what you see is that the shape of both the voltage and the electric field have changed quite a bit. Now what we see is that the voltage divides almost evenly running down the middle. That is, the color is changing uniformly down the center. And again, referring back to the formula page that we looked at, you can think of this in terms of current flow. There is a current that is flowing, and it's the conductive current that's dominating in order to change this from the permittivity answer. So there is a current flowing down the middle, and there is a pretty close to uniform electric field down the middle associated with that current flow. There is no current flow out in the sheds, and therefore each shed maintains pretty close to the same voltage as the material right beside it where the current actually is flowing. By creating a voltage division that runs down the side more or less uniformly, that means that now the field is much lower around the side of the cap, but much higher out at the tips of the sheds and in between the sheds. So the question of whether this is a good or a bad dielectric is going to be seen to depend largely on the combination of the permittivity, but especially the conductivity and the frequency. If we change to a different frequency, again referring to our formula that the imaginary part of the dielectric constant is the conductivity divided by the frequency, we will of course change the balance between real and imaginary parts.